Hello, this is Alessio Mansutti, and this is a joint work with Bartosz, Bednarczyk, Stéphane Demri, and Raul Fervari. So I will start with one slide that summarizes a little bit the idea of our work. In recent years, we saw a lot of logic that try to reason on resources in a modular way. And perhaps the queen of these logics turned out to be the logic of bunched implication by Peter Hearn and David Pym. Now, the central feature of BI is given by a composition phi.psi that states that given my resource, here for example an apple, it can be split into two pieces, one satisfying phi and another one satisfying psi. Here is where the modularity of BI comes from. I can now split a structure and reason on each piece modularly. And from this simple idea, a lot of logics were developed. But perhaps the most known instantiation of BI are given by ambient logic and separation logic. Now, ambient logic is a logic for verification of concurrent systems specified in ambient calculus, whereas separation logic is perhaps the most known logic for verification of sequential programs and concurrent programs manipulating pointers. Now, both these logic instantiate BI, but they use their own composition operator, and modulo some difference in the models that they are used, the composition operator is the main difference between ambient logic and separation logic. And in this paper, what we want to address is to compare the star and the chop of separation logic and ambient logic in terms of complexity and expressive power. Now, let us start with a summary of ambient logic and separation logic. Ambient logic is interpretive information trees that are trees from this grammar here. 0 stands for the empty tree. N of t stands for a tree where the root has only one child, labeled n, and then this child has a certain subtree. And then instead, the parallel composition here does the union of trees, which means that actually the root of the two trees will be merged. So for example, this expression here on the left corresponds to the tree on the right, where the parallel composition at the beginning state that on the left I have a tree where the root has only one child, labeled A, whereas on the right I have a tree that where the root has only one child, labeled B, that have two children, B and A. Now, the ordering of the children does not matter in ambient logic, and that's why the trees are taken up to a certain congruence that specify that the parallel composition is associative, commutative, and that the 0 is the identity element. Now, from this parallel composition, then in the logic, we have the chop operator. And the chop operator instantiates the operation of BI, stating that a certain tree satisfies phi chop psi if the tree can be split into two trees, T1 and T2, T1 satisfying phi, and T2 satisfying psi. Now, one thing that I want you to notice is that the splitting in ambient logic is on the root, meaning that I need to, in a sense, partition the children of the root into two colors, here yellow for T1 and blue for T2, and once one of these edges is colored in blue, then all the subtree will be blue or in T2. Now, this is something that does not hold in separation logic. Separation logic is interpreted on memory state, where S is a store that here we don't care about, and H is a heap that is a finite functional graph. So essentially, you can see it as a forest where the root of the forest can actually loop back to one of his descendants. And then separation logic introduce a concept of union of heaps that in a sense corresponds to coloring your heap with two colors, one for one heap and one for another heap, arbitrarily, meaning that if one edge is colored in yellow, then I don't have any information on the color of the other edges. And from this union of heaps, exactly as in ambient logic, we will have an operator that is the star in separation logic, and a star state that a certain memory state satisfies phi star psi if it can be split the heap into two heaps, H1 and H2, such that the memory state SH1 will satisfy phi and SH2 will satisfy psi. Now, I want to repeat the main difference. In ambient logic, if a children of the root is color of a certain color with the edge, then the whole subtree will be color of the same color. In separation logic, instead, the coloring is completely arbitrary between the edges. And here, this is exactly what we ought to study on a computational level. What is the difference between these two types of operation? We approach this problem from the point of view of modal logic on finite forests. And we use modal logic on finite forest because it will give us a framework that is general enough to compare the chop and the star, but is also close enough to both ambient logic and separation logic, so that then we can transfer back the result to these two logics. And we introduce two modal logics. One is modal logic chop, which is modal logic, standard modal logic with the composition from ambient logic. And one is ML star, which is modal logic with the star from separation logic. And in terms of expressive power and complexity on finite forest, we find that ML chop, so with the ambient logic composition, is as expressive as graded modal logic, whereas instead its satisfiability problem is AXPOL complete, where AXPOL is short for alternating exponential time with polynomial in many alternation. On the other hand, ML star is shown to be non-elementary decidable in terms of its satisfiability problem, more precisely tower complete, where tower is short for a tower of exponential whose height is a function that is elementary compared to the input sides. Very surprisingly, the expressive power of ML star sits between modal logic and graded modal logic, and in particular is less expressive than graded modal logic, so less expressive than the chop operator, even though, I repeat, ML star is more complex in terms of satisfiability problem. And lastly, for these results on ML chop and ML star, we are able to close some open problems in both ambient logics and separation logic. So let us formalize ML chop and ML star. As I said, we want to use modal logic and finite trees. So our model will be Kripke style finite forest, meaning finite forest with a current word or node W, and then where every node is enriched with an evaluation for atomic propositions that here I just abstract with colors. And in standard ML, we have propositional calculus plus the diamond modality stating that from my current node, I have one child satisfying the formula phi. So for instance, this formula here states that for my current word, W, I have one child satisfying not green, that has one child satisfying blue, so it is true in this model. Now to get ML star, we use the standard construction from bunch implication and simply specify what is the composition that should be the composition of separation logic. So in a sense, given your model, you must be able to color its edges in two colors, orange for the submodel M1, black for the submodel M2, such that then M1 satisfies phi and M2 satisfies psi, and the coloring is arbitrary, as in separation logic. Now ML chop is different, and just in terms of the composition. Given your finite forest, you must still color it with two colors for M1 and M2, but now if from the current word I color one edge leading to a children in orange, then the whole subtree rooted at the children must be all orange, must all be in M1. And this is the only difference between ML star and ML chop. And one thing that I want you to notice is that since we are in modal logic, after the splitting takes place, if a part of the model is not accessible from the current word, it doesn't affect the evaluation of the formula, it doesn't affect the satisfaction of the formula. So it can be removed, and what we obtain are trees that is the same models of ambient logics. Now, we can easily see ML chop and ML star as fragment of monadic second order logic on finite forest, because both the star and the chop operator essentially color the structure, which is something that we can do with monadic second order quantification. This means that the satisfiability problem of both ML chop and ML star is decidable in tower. Another easy connection that we can do is between ML chop and graded modal logic. Now, if I give you this formula here on the left, it states that your finite forest can be split into three pieces, each of them where the current node has a child satisfying phi. So for example, for this moment on the right, the splitting can take place in this way. Now, this corresponds to the graded modality diamond greater or equal than 3 phi from graded modal logic, where I recall that graded modal logic is just modal logic with a suite of operator of this form, diamond greater or equal than k phi, stating that the current word witnesses at least k children satisfying phi. So then the natural question is, what if ML chop is as expressive as GML? And this is what we show in the paper. We show that given two formula phi1 and phi2 in GML, there is always a formula gamma in GML, such that gamma is equivalent to phi1 chop phi2. So some ingredient of this, let us pick this easy example. We have a formula that states that I can split my finite forest into two finite forests, the left one being such that the current word witnesses a number of children satisfying phi that is between 3 and 6, and the right one say that the current word witnesses at least 2 children satisfying phi. This formula is equivalent to the graded modalogic formula diamond greater or equal than 5 phi. Now, how we do this translation in a methodical way, we go through Pressburger arithmetics. We start by seeing the expression diamond greater or equal than k phi as the expression x phi greater or equal than k from Pressburger arithmetics, where now x of phi is interpreted as the number of children in my finite forest satisfying phi. Then we internalize the semantic of the chop operator directly in Pressburger. So for instance, instead of saying that there are two models M1 and M2, we'll say that there are two values for the variable y phi and z phi, where now y phi stands for the number of children in M1 satisfying phi, and z does the same for M2. The chop operator here, m equal M1 chop M2, becomes the expression x, so this is the number of children in M satisfying phi, equal y plus z, and then the expression of graded modal logics, we treat it by simply replacing the expression diamond greater or equal than k phi with the equivalent expression for Pressburger arithmetics. Lastly, the chop operator simply becomes a standard conjunction. Now, when we do quantifier elimination of this formula, it will lead always, and this is what we show, to a formula of the form x greater or equal than a certain k. So we don't have modulo constraint or other type of constraint for Pressburger arithmetics. We always have some x greater or equal than some k, and in this case we get exactly the formula that we want for Pressburger arithmetics. Now, there are a lot of things that I'm hiding here, and perhaps the most interesting one is that phi and psi in a formula divided by the chop, like this one here, can be such that their conjunction is satisfiable. Or even better, suppose that phi entails psi. So then in a solution of the Pressburger system, what I would like to have is that x psi is always greater or equal than x phi, in the case that phi entails psi. But now what we did in the paper is that actually we can manipulate the formula before removing the chop operator, such that phi is always syntactically equal to psi. So then in the Pressburger system, this will lead to just one variable, x phi, or such that phi and psi is unsatisfiable, meaning that then in the Pressburger system, x phi and x psi are completely independent. The cost of this manipulation of the formula is one exponential blow-up, but this is all there is, meaning that we also proved that then the formula that we get from Pressburger arithmetics has an exponential size small model property, meaning that then ML chop has also an exponential size small model property, and from this property we can easily deduce that the satisfiability problem of ML chop is in X-pole. Now what we will do is that we will simply see the formula as a formula from MSO on finite forest. We will guess the finite forest or exponential size following that the small model property, and we'll apply model checking from MSO. Now since we are doing it for an exponential size model, it will be in a x space or a x time, and then we will do polynomial many alternation because there are only polynomial many negation in a formula phi. For the hardness, we'll show in the paper that the satisfiability problem of ML chop capture the satisfiability problem of propositional team logic, where propositional team logic is another instantiation of BI. And more precisely, formula of propositional team logic corresponds to formula in ML chop of model depth 1. Now, the completeness with respect to X-pole of propositional team logic is known from 2018, and from this we will get that SAT ML chop is X-pole complete. Let us now move to ML star. Now we already saw that this formula here of ML chop is valid, and so for instance this instantiation is also valid, where phi is just diamond equal 1 blue. Now this formula here is valid, but when I remove chop and replace it with a star, I obtain a formula that is not valid anymore. and this is a counterexample. Here I will have this red node on the left that has two children that are blue, meaning that now the formula on the right is not satisfied. But then among these two children, I can put one on the model on the left, the other on the model on the right, and obtain two forests that satisfy the two formula here on the left. Now, as I said before, this node here, this red node on the right, since it's not accessible from W, can be removed from the extraction without affecting the satisfaction of any formula. And if we do so, we obtain two forests that are in the chop relation. Now, when I combine these two forests, I will obtain a forest that is can be obtained from the original one by removing some descendants of W that are not children. Now, the interesting thing is that this operator of removing descendants but that are not children can be characterized in ML star and corresponds to the formula phi star box bottom, where box bottom essentially say that I can have some descendants of W but not its children. So he's exactly doing this operation here on the left. And this leads to the following equivalence, saying that phi star psi is equivalent to first removing some descendants that are not children with star box bottom, and then using phi chop psi. Now, this equivalence will lead us to prove that actually ML star is at most as expressive as GML. And to do that, we simply show that GML is closed under the operator star box bottom. And we do that by using standard techniques from model theory. We'll start by considering the G by simulation, that is the by simulation but for graded modal logic. And the essential property of G by simulation is that two G by similar model are such that they will satisfy the same graded modal logic formula, where here the indices M, K, and P stand for what is the maximal modal depth that a formula can have, what is the maximal coefficient, and what atomic proposition I can use. So once we have this indistinguishability relation, we apply a standard simulation argument. We will say that there exists a function which depends on the modal depth and on the coefficient of the graded modalities, that when two models are G bisimilar with respect to M Fk of MP, so using this function, then for every way I have to use the starbox bottom operator to remove some descendants of my model on the left. So here I can have that the children of W can jump around in different equivalence classes of the G by simulation, and we start satisfying other formula of GML. For every way, regardless, for every way I have to do this split on the left, there is a way to do the same thing on the right that will lead to a model where the children have the same profile with respect to graded modal logic formula, and so the two models on the left and on the right will be G bisimilar with respect to M, K, and P. Now, the main problem is what is this function? And in the paper, we show that this function exists, is non-elementary, and it depends on the number of equivalence classes of the G by simulation. So now, to do this, we used a non-elementary function. But what if we were not careful enough and there exists one that is elementary? So then we will probably be able to show that ML star is elementary decidable. Unfortunately, this is not the case. And in the paper, we start by noticing that we characterize in ML star node of type K with a formula that is exponential in K. Now, a node of type K is a notion that was already introduced at LICS last year for quantified modal logic, which is a modal logic featuring second order quantification. And among other properties, a node of type K will have a non-elementary amount of children, a Tower amount of children. And now I will explain a little bit what is this node of type K, because it could be applied to other similar modal logics. So a node of type 1 is just a node that have two children, one satisfying B and one satisfying not B. And we can see these two children as a 2-bit number, where the one satisfying not B is the least significant bit, and the other one satisfying B is the most significant bit. Now the node of type 1 will also encode a number by simply looking at the value of another propositional symbol that here I just represent with a black dot. So for example, this type 1 node will encode the number 0 and 1. Now what is a node of type 2? Will be a node where every child is of type 1. Every child encodes a different number, and since they are of type 1, it will be 2-bit number. And every number is coded by a child. So this will lead to this structure here, where I have exactly 4 children, going from the value 0, 0 to the value 1, 1. And this can be seen now as a 4-bit number. And of course, depending on the truthiness of the value represented by the black dot, I will obtain a certain number for the node of type 2. Here, for example, 0, 1, 0, 1. Now, a node of type 3 will have to do the 4 children, because I will have 4 bits number for every possible values, and it will code itself a node between 0 and 2 to the 2, 4 minus 1. So in general, a node of type k will have f of k children when f is the iteration function of base 2. Now, characterizing node of type k in ML star is quite tricky. First off, we don't have second-order quantification a la quantified ML. The star is strictly less powerful than second-order quantification. And also, we know that we are encoding the numbers inside nodes using the children and descendant of that nodes. And we know that the star will break the accessibility relation if not handled correctly. And so we will not be able to retrieve the number that a certain node encodes. Regardless, in the paper we show that this can be done. We can characterize word of type k. And afterwards, once you have that formula that characterizes words of type k, it's easy to actually extend it a little bit so that a single node will have now a pair of numbers. So then from pairs of number, we will be able to encode a grid. And from this grid, we will be able to have an uniform reduction from the k next time version of the tiling problem for every k greater or equal than 2, where the formula will just be exponential in k. And this will lead to the tower hardness of the satisfiability problem of modal logic star. So let us recap what we did in the paper. We introduced two modal logic whose sole difference is that one ML chop used the chop operator from ambient logic, and the other we use the star operator from separation logic, that is ML star. The expressive power of ML chop is the expressive power of graded modal logic, and its complexity in terms of satisfiability problem is complete for the class alternating exponential time with polynomially many alternation. ML star instead is tower complete, so non-elementary, and in the slides I show you that is not more expressive than graded modal logic. Actually, in the paper we show a little bit more. We show that actually ML star is less expressive than graded modal logic, and we do so by RFRofessor games for modal logic star, showing that this simple formula saying that I have two children that have exactly one children cannot be expressed in modal logic star. Using ML chop, we are then able to also show that the quantifier-free intentional fragment of ambient logic is X-pole complete, and that the ambient logic introduced in this paper from 2003 is X-pole hard. And I want to stress a little bit this because in the conclusion of this paper, the author believed that actually this logic was p-space complete. Instead, for ML star, we are able to use the result on the satisfiability problem of this logic to show that the modal separation logic star diamond minus 1 introduced in Advancing Modal Logic 2019 is tower complete. Thank you for your attention.